You're going to have to move to the front, and I promise I won't bite. Okay? So it's a great pleasure for me to be here, and it's a particular pleasure because I was here at the ANS Laboratoire de Physique Statistique as a very young boy visiting my brother who was here, whom I actually had dinner with last night here in Paris. And he told me, he was a little bit nervous about me giving the talk here, so he said, "You know that this is a big deal, right? A talk at the physics of the École Normale." So I am sure that it is a big deal, and I'm very grateful to be able to be here. So I will talk a little bit about our work on graphene, and I say putting graphene in a microwave. It's not really microwave, it's terahertz. And I'll show you that there's good things about putting graphene in a microwave, and there's bad things about graphene in a microwave. And I'll start with the bad things, and I'll end with the good things. Before I start, however, I have to acknowledge several people, but in particular Dimitri Turchinovich, Frank Koppens, Michael Gensch, and Klaas-Jan Tielroy, who were all major contributors to the work that I will be talking about today. So I will talk about graphene. I will very briefly introduce graphene. This is the structure. I think you know all that and all know that. It's a semi-metal. It has a zero band gap, which means that it can absorb light at all frequencies, and the linear dispersion relation gives rise to very high mobility of charge carriers in this material. So it's an interesting material for electronics. Now, if you put graphene on, say, a silicon dioxide substrate, one thing you have to realize is that it gets doped. And so the Fermi level, which was originally at the Dirac point for suspended graphene, for supported graphene, you actually dope it with about 10 to the 12 dopants or electrons or holes per square centimeter, corresponding to a Fermi energy of about 200 millivolt. And this means that graphene, when you put it on a substrate, is intrinsically conductive. And this is what we're interested in. We're interested in the conductivity of graphene. And I'm going to show you that you can, of course, put a contact, two contacts on graphene and apply a field and measure the current response of the material. This you can do, but I'm going to show you that there's another way of measuring the conductivity which is nice and useful, which is using terahertz spectroscopy. And rather than applying a field for a very long time, seconds, you can apply a very quickly oscillating AC field, and the oscillation time is about a picosecond. And the nice thing is that you can do this optically. So it just involves a lot of mirrors and laser beams. It doesn't actually involve contacts. And I'll show you that this is of great benefit. So the other thing, of course, is because this pulse is very short, it means that we can have very high time resolution of about a picosecond, which is also useful. So this technique is ultra fast, contact free, and I'll show you it's a quantitative way of measuring conductivity in any material, and in this case in graphene. So when we do a terahertz experiment, this will force me to show you how bad I am at PowerPoint animations. So please bear with me. This is the terahertz pulse going through a bare substrate, and we're going to compare the terahertz pulse going through a CVD grown graphene on a substrate, which I've told you already has electrons in it or on it. And so when we do that, the one pulse doesn't do anything. The other pulse accelerates the electrons in the material, and that causes a reduction in the amplitude and a phase shift of the pulse. And that reduction in the amplitude is a direct measure of the real conductivity of the material. And that real conductivity, again, is a product of the number of carriers that we have in there and their mobility. And the phase shift that you see is a measure of the imaginary conductivity, or the polarizability that is induced by the presence of these free electrons. So how does that work actually? And this is important for the rest of my talk. It's actually very simple. The incoming terahertz pulse, by accelerating those charges in graphene, generates a current. Now, and you all know from your electromagnetism class that a current will emit a field, and that emitted field is proportional to the time derivative of that current. And so what happens is that this current is out of phase with the driving field, and that gives rise to essentially interference and a reduction in the terahertz pulse. And so you can imagine, and I don't want to go through the whole derivation here, but I want you to understand that by taking the difference between these two, we have something that's proportional to the time derivative of the current. And so we can backtrack from that, of course, the conductivity. All right? So if you have any questions, yes, please. Chemical vapor deposition. Yes, it's a way to make graphene, large area graphene. Any other questions?
So the reduction in the pulse amplitude means it's lost energy. Is that
Yes.
going to motion of the electrons, or is it dissipated? Is it measuring the imaginary part of the conductivity?
The loss in the amplitude is indeed dissipated. There's some energy dissipated in the system, and what happens is that the electrons will scatter off of phonons, and that is what is giving rise to the decrease in the amplitude, effectively.
So it's measuring the resistivity?
Exactly. Yep. Going once, going twice. All right. So again, this is just to illustrate again how bad a PowerPoint animation guy I am. So this is what we were seeing, and this is why the change allows us to get the real and the imaginary part of the conductivity. I don't know why this is showing up again. I also don't know why this is showing. Anyway, so what we do now is we analyze these, they're called waveforms, in the frequency domain. So we Fourier transform essentially the difference of those two, and that gives us the conductivity as a function of all the frequency components that are contained in that waveform. So this gives us the frequency-dependent real and imaginary conductivity of a monolayer of graphene. Okay? So that is informative because we can describe the lines that you see here are a simple fit to the Drude model, which essentially only has two parameters: the plasma frequency, which is proportional to the number of electrons, which is a quantity that we can determine independently from Raman measurements, and the curvature and the crossing point of these two lines directly give us the scattering time of the electrons in the graphene. And so for this particular graphene, this is good graphene, the scattering time is 140 femtoseconds, so that's where these two lines cross. And given the velocity, the Fermi velocity of electrons in this material, that means that the mean free path is about 140 nanometers. So that's all nice and good. So when we started investigating graphene, we actually wanted to measure the photoconductivity. So now I've shown you how we can measure the steady state conductivity, but we were interested in measuring the photoconductivity. And so we photoexcited the graphene. And the idea that we had initially was quite naive, was that will generate additional carriers, free carriers, and that should increase the conductivity of the graphene, like with any semiconductor. Now, we were very surprised that when we did this experiment, so now we are comparing the photoexcited case with the non-photoexcited case, and again, my beautiful animation, what we saw was schematically depicted here that there was more light coming through the excited graphene than through the unexcited graphene. So we have we have a lowering of the resistivity essentially in the graphene because we photoexcited, and that was very puzzling and we were actually not the only ones to see this. So this means that we have a negative photoconductivity. And at this time, this is a few years ago, there were people that say, oh, this graphene is a terahertz gain medium, and this is beautiful, and well, it's not a terahertz gain medium. Really what is happening here, this negative photoconductivity is very simple, that you photoexcite electrons, they scatter very quickly amongst themselves and amongst the electrons that are there because of the doping, and you get within about 10 femtoseconds, you get a hot electron distribution. So you get a Fermi direct distribution that is now hot, and those hot electrons simply have a reduced conductivity. And so there's no magical gain, or there's nothing special about this. It's just the optical pulse heats up the electrons that are there due to the doping, and they have a reduced conductivity. So, having said that, that actually brought up a question. So, we've solved that because it was as very high. You can get up to 100% conversion from the photon energy into this electron heat bath. So there's not a lot of phonon scattering involved because it's essentially so fast. So we thought that is wonderful for photodetectors, but there's actually a problem with this, this heating of carriers and the reduced conductivity. And that problem is very nicely illustrated by the progress that has been made over the years in ultra-fast graphene-based transistors. And so here's a plot from 2013, but not much has changed, and I'm going to explain to you why not much has changed. And you see that here in these green triangles are graphene-based transistors, and they actually cannot compete with normal semiconductor, bulk semiconductor-based transistors. And the question was, why is that? Why can you not, this material is so superior in its conductivity, and it's so thin, and it's a monolayer, and it's so great. Why can you not build a better transistor from that? And so this is essentially time, and we got stuck, the community got stuck at about 0.4 terahertz, 400 gigahertz. And so that is the world record. But if you look at the gate length here, so this is 100 nanometer, and if you consider that you have to apply, say, roughly a volt over 100 nanometer, then you realize that you have field strengths of 100 kilovolt per centimeter in your field effect transistor. And these fields are very high. And I showed you that this optical excitation can give rise to heating because of this electron-electron scattering, and that reduces the mobility, the conductivity. So the question is not the same thing happening here when you apply these fields at, say, 0.4 terahertz frequencies? And so the question, and that's the research question, this was all just an introduction. The research question that I want to address today is, how does graphene respond to an external AC field, essentially? And we're going to investigate how that affects the conductivity of the material. And I'm going to do two very simple experiments. So we're going to take CVD-grown graphene, and we're going to look at the transmission of a tabletop terahertz pulse, which has this single cycle that I showed you before. And we're going to look at the transmission of a pulse from a free electron laser, which has a better defined frequency because it has many more cycles of the field, so it's a more narrowband pulse. And we're going to see how that affects the electrons and how the electrons affect the optical response. And so the first experiment is to transmit this tabletop pulse and to increase the field strength and to see how that affects the conductivity of the material. And so the experiment is very simple. We go from 7.5 to about 200 kilovolt per centimeter field strength, and we are going to simply measure how that pulse itself affects the conductivity of the graphene. So it's a so-called pump-probe experiment, but with just one pulse, where we just use the transmission of the same pulse. This is the spectrum of the graphene, of the terahertz pulse. And so it's nicely in this region where we have the cutoff frequency, and the next generation graphene-based field effect transistor should go up to, say, terahertz. So we're in the right range. And I told you already that for these field effect transistors, we have field strengths of about 100 kilovolt per centimeter. So we're in the right range there too. So at low fields, so this is the real and imaginary conductivity as a function of frequency for low field 2 kilovolts per centimeter. And I already showed you this plot, so these two cross somewhere here, and this is this 140 femtosecond scattering time. So now we're going to increase the field strength and let that report on the conductivity that we measure. And what we find is that if you increase the field strength, and you don't have to increase it much, so if you go to 30, 40 kilovolt per centimeter, the real conductivity at terahertz frequencies drops dramatically. And this is probably the reason why there has not been a high frequency graphene-based field effect transistor. Because as soon as you make a field that is needed in those small transistors, the conductivity drops. And so what you see, the lines here are fits to this Drude model that I showed you before, and you see actually a drop in the conductivity. So I don't want to go into too many details, but actually what you see is that the scattering rate decreases. So the mean free path increases. But this is a whole different story. The important thing is that the conductivity drops. And the reason for that, of course, is that you simply get hot electrons. So in the same way that the optical pulse heated the electron bath, the terahertz pulse accelerates an electron, that electron scatters with other electrons, and the whole electron bath heats up, and the conductivity is reduced. And so as we go to even higher field strength, you can see that really the conductivity goes to zero, essentially. The conductivity at 1 terahertz. And so you can really, by applying these high fields, you can really kill these beautiful properties of graphene with moderate fields, in fact. So the high field conductivity actually saturates. The lines that you see here are a very simple model that we implemented, where we said, okay, this terahertz pulse has an energy of about a microjoule. We know that the graphene absorbs about 5% of that pulse, so we know how much heat goes into the electronic heat system. We know the heat capacity of the electronic heat system, so we know the temperature of the system. We're not changing the carrier density, we're not injecting carriers, we're simply heating up the electron bath, and so this has nothing to do, well, you can describe all the electrodynamics simply by thermodynamics. It's really quite a simple model, and that describes the data very well up to very high field strength. Yes?
Sorry. So it means that you can basically replace the electric field with an effective temperature. The effective temperature controls.
Exactly.
What is this? So this effective temperature is basically filled over whatever dissipate.
Yes.
And how hot is it?
So it's thousands of Kelvin. And the reason for that is that the specific heat of the electrons is very low. So with relatively little energy, you can heat the electron bath a lot.
Thanks.
Do I have to drop the microphone again?
Yeah, please just request it.
All right. So the high fields in an FET basically kill the conductivity, and this is a problem if you want to make a graphene-based field effect transistor. So these were great properties, and high fields are a bit of a problem, but you can also turn it around, because it's not it's a bug if you want to do electronics, but it's a feature if you want to do optics. And so I told you that what we do when we apply this electric field is we drive a current, but I've now also shown you that already at modest field strength, this current heats up the carriers, which reduces the conductivity. And so you get some sort of interplay between the external fields, the electrons that are heated and can cool again, and the current that is driven by that field. And it's, of course, that's a very nonlinear effect, because the higher the field, the more this current starts to saturate. And so the E field drives the current, but also changes the current. This current emits an electric field, but if the system responds very nonlinearly to the incident E field, then this emitted field will contain harmonics of the fundamental. This is a very nonlinear system in essence. And so nonlinear optics, here we come. This is a great system to do nonlinear optics. And so this is why we went to the free electron laser, because if we're going to do look at harmonics that are being generated in the graphene, we need a good narrow spectrum. And this has a very broad bandwidth, so it's relatively difficult to distinguish the fundamental from the higher order terms. And here it's very easy. And so that we can get this nonlinear time-dependent conductivity is apparent from this measurement here, where we did a terahertz pump, terahertz probe measurement. So now we get just like with the optical excitation, we get basically a reduction in the terahertz photoconductivity, if you will. And so this is basically the terahertz excitation pulse that is heating up all the carriers, that is reducing the conductivity, and this modulation is several percent, and then the carriers cool and the system regains its original conductivity. And so this heating occurs very quickly, and the cooling occurs on this time scale here of about a picosecond. And so the idea of using graphene as a harmonic generator is to say, okay, we come in with an incident terahertz field of frequency f. That field drives a current, but that current is now very nonlinear, because we know when the field is high, the electrons are hot, and they will not emit, therefore the current will be reduced and it won't emit as much terahertz. And so what we hope to see is a nonlinear current that emits some sort of harmonic of the incident field. That was the idea. And so this relies on a very strange effect, namely that during the cycling of the terahertz pulse, you get cycles of heating the electronic distribution. So it looks like this, and we have this greatly reduced conductivity. Then between cycles, essentially, cooling takes place, because the oscillation time here is about a picosecond. So there's substantial cooling occurring before the next cycle of the pulse comes, which heats it again. So you keep going through these cycles of heating and cooling and heating and cooling. And this is what gives rise to the nonlinearity. And so this is what we then see is actually not only the third harmonic, but I'll show you also even the fifth harmonic and the seventh harmonic of the incident field. And the raw data actually already shows you, so this is the black and the red are measured at different incident field strengths, and the blue that you see here is the difference, and you can see the harmonics in the signal itself. So this works extremely efficiently. And so what you see already from this measurement here is that you get for, this is a 10 microjoule pulse, you get about 10 to the minus 3, 10 to the minus 2 conversion efficiency. So very high conversion efficiency. And you have to realize that this is all occurring in one atomic layer of material. So this is not a bulk crystal, this is just one layer. And so this is the, in red you see the excitation pulse, and then in blue you see these different harmonics, so the third, the fifth, and the seventh harmonic of the terahertz being generated. And you see that we get field conversion efficiencies of % in this way. And again, I can't stress this enough, this is a single layer of material. So we get a conversion of 1% of the field from the fundamental to the third harmonic in one layer of material. This is quite high. And so if you compare that to what you would need for other types of mechanisms, your orders of magnitude more efficient here. So these are the inferred third, fifth, and seventh harmonic fields. We can actually understand the phase relation between these different fields. We can also understand, again, through this simple thermodynamic model of heating and cooling and knowing how the conductivity changes when the heating occurs. We can model this, and I don't want to go into too much detail, but you can see that we really understand what is happening, and we can really quantitatively reproduce the harmonics that are being generated, again, by this simple model of electrons being heated by the field in this terahertz pulse, and then as the field switches off, the electrons cool, the conductivity goes up again, then the field changes sign, the carriers are accelerated and heated, and the conductivity goes down again, and then as the field goes to zero again, and it's on and on through this cycle. And so this is, the lines are again this thermodynamic model. There are no fit parameters in this model, so this is just, we know what goes in, we know what goes out. And then you can see that the effective third order, and fifth and seventh order susceptibilities are up to 10 orders of magnitude larger than nonlinear optical crystals that you would use to generate second or third harmonic. And the reason for that is this fundamentally different methods of harmonic generation from these crystals. So here I try to compare, this is a fancy picture of a terahertz pulse hitting the graphene and generating all these colors. And as I've told you, this is an extremely efficient process, and the reason is for this high nonlinearity is that we have these free electrons. These free electrons that can be accelerated, that respond extremely nonlinearly to this acceleration in a collective way by heating up, and then cool. So they have a very large polarizability, because free electrons have a very large polarizability, and they have a very strong nonlinearity, which is exactly what you need for nonlinear optics. If you compare that to a nonlinear crystal, like many of you who do laser spectroscopy work with BBO crystals or lithium niobate crystals, those nonlinear susceptibilities rely on the nonlinear displacement of electrons, of electron wave functions that are bound electrons. And so it's not a surprise that those have a much smaller polarizability and that you need to apply much stronger fields to get into the nonlinear regime. And so this is what allows this very high conversion efficiency in the monolayer graphene. So with that, I'd like to conclude, and I hope I've shown you that this high harmonic generation is very efficient. We did all these experiments at room temperature, so it's just works extremely well. It's enabled by this collective heating and cooling of carriers, very simple physics underlying, but which is really fundamentally different from normal ways of harmonic generation in materials. And these, as a result, the effective nonlinear coefficients are many, many orders of magnitude higher than those in conventional nonlinear materials. So I've shown you that the reduced conductivity of hot electrons is a problem for devices, but you can use that same reduction due to heating to drive these high harmonics in exactly the same material. So it's a bug here, but it's a feature here. And with that, I'd like to end and thank you for your attention.
So you see the odd harmonics. So I guess the way the electrons cool after excitation. But can you get even harmonics, or is it something should be even higher nonlinearity if you can get even harmonics?
So you cannot get even harmonics because of symmetry breaking. That is the symmetry. This is a centrosymmetric. Graphene is a centrosymmetric material, and so the second harmonic and fourth harmonic signal are not dipole allowed. So you will generate locally very high second and even order, higher even order polarizations, but for each polarization that you create in one direction, there will be another that cancels it out. And so the net in the far field, you see really nothing. I mean, there's really nothing there.
Thank you very much. Can you tell us what happens in the valence band for the electrons? You said when you apply the pulse, then you heat up the conduction band. But what happens to the holes that remain in the valence band?
Yeah, so everything that I said is completely symmetric around holes and electrons. So we have no way of distinguishing between the two. And so I only talked about electrons, but I should have indeed said I can replace the word electron by the word hole in my whole presentation. And it's, as far as we can tell, completely symmetric. But it's a good point.
I understand the hot electron picture and the thermodynamic machine, but this mechanism is would be also true for any metal that you would heat with some electric field. Any metal you would drive an electric field, it would heat up, and so the thing that really makes your story special is about those harmonics and these coefficients that are higher for graphene, presumably than for higher materials. Why is it? Why is it that graphene has this?
So there's a couple of reasons. The mobility of graphene is the electromobility of graphene is very high, much higher than in most metals, and so the conversion of the field into heat essentially is very efficient, and is much more efficient than in a metal, which also has much stronger electron-phonon coupling than graphene. So you will very quickly also start emitting LO-phonons that will heat the whole lattice. So all these problems don't exist in graphene. So high mobility, high nonlinearity, and very little electron-phonon coupling. Those are I think the main effects.
You told us that when you heat up the electron bath, then the mobility decreases.
Right.
Why would it decrease if you don't have any phonon?
Yeah, that's a very good question. So it's actually, I don't, so the weird thing is, as you see here, so the conductivity goes down, right? And which means that this, and you see that this doesn't change so much, so the crossing point goes to lower frequency, which means longer scattering time. And so as you heat, that's what you see here, as you heat the electrons, the scattering time gets longer. And so there are different ways of explaining why that leads to a lower conductivity. In essence, it has to do with the very peculiar band structure of graphene. And related to that, what you can see here is that the DC conductivity is fixed, it's pinned. And as you heat up the electrons, you have you have spectral weight conversion, so you cannot get additional overall absorption, and you get extra interband transitions at higher, right? Here at much higher frequency. And so the spectral intensity has to drop here. So the conductivity has to drop. This is one way of explaining it, but I do not have a compelling physical picture of why that is. So in a metal, of course, you heat it up, the scattering rate increases, the mobility increases, life makes sense. In graphene, the band structure is such that you heat it up, the scattering rate decreases, and yet the conductivity decreases.
So the cooling rate, is this on? The cooling rate is an important quantity in your experiment. Is that something that depends on the environment in which the graphene is located? Or
Yeah, that's a very nice question. So if you think about, so I've shown you this, right? This is essentially really the cooling time that we can measure. You can also measure it optically. I also showed you the optical experiment. It's roughly a picosecond. And if you think about this high harmonic generation, then we do it at 300 gigahertz and not at higher frequencies, because at 300 gigahertz, between the peaks and valleys of the field, there's enough time for the system to cool down. And so what you would really like is you would like to push this into the IR, but then you need faster cooling. And so we're now trying to look at how doping or sandwiching the graphene to maybe use different cooling mechanisms, how that might allow us to push this into higher frequencies. So that's a very good point. That's limiting the frequencies that we can get out to.